Hi! In this video, I'll be going through what are linear transformations, and throughout more videos, we'll take a look at how the basis that we learned in the previous video applies to this video. So first, let's define the linear transformation, and a linear transformation from two vector space V into W is a function that satisfies this linearity property. So it means that you take a linear combination of any two vectors, then the linear transformation preserves it, this linear combination. So for example, you have a vector which is C alpha plus beta, and you run it through the transformation, which is the function. It will be whatever the output is of C T alpha plus T beta. An example would be the identity map, as you can check that this property holds, and the zero transformation is a trivial one that is of course a linear transformation from V into V. Some other examples to familiarize ourselves will be if we take the space of all polynomial functions, then this is a polynomial function, then the differential operator will also be a linear transformation, as you can check that this property holds, because when you differentiate, say C alpha plus beta, this you can check that C alpha plus beta, the polynomial will of course be C naught plus A naught plus C1 plus A1 alpha x, then all the way, and then when you differentiate, you can rearrange it, and it should be clear that it is a linear transformation. Some other types will be, for example, the matrix multiplication function is also a linear transformation. So you first have a matrix, and your function is just taking that matrix multiplied with x, where x is a n times 1 vector. Then it'll go into a m times 1 vector. So the function is defined by alpha a, and it's another linear transformation from now fm into fn. So it's important to note that if t is a linear transformation, then t0 must always be 0. And this is because t0 equals to t0 plus 0, and when you expand out, it will be t0 plus t0. So you cancel off, this must equals to 0. And in addition, the transformation preserves linear combination, as I've said. So here's the more generalized version. So now let's take a look at how it plays a part in the basis. If we have a finite dimensional vector space, and we just let alpha 1 to alpha n be an ordered basis for V, and W be any vector space with some set of vectors, then there's only one unique linear transformation from V into W, such that this property is held. And if you just think about it, it just means that to prove this, you just need to take an alpha from V, then it must have a unique tuple created by all the alphas 1 to alpha n, because this forms an ordered basis, and this will just be of course the column vector. For this vector, we can just define T alpha now, because it preserves linear combination. it has to be this. And this will be the only definition that is available. And with that, it also gives us the property that we want. And it is not hard to check that this function now is a linear transformation because the linearity property holds. And so, any other linear transformation that has this property, then the vector equals to this. So u alpha must equals to u of this sum, which is the same in the end. So you can see how this will be the only vector and the only linear transformation, and so this linear transformation is unique. So some more examples follows as let's just say you have two vectors 1 2 and 3 4, and you want to show, and these are linearly independent and therefore they will form a basis for R2. So based on that, we have a unique linear transformation from R2 into R3 such that when you take this, it gives you this coordinate and this coordinate gives you 6 5 4. And as such, we must, and because of that, we can also find what is T of the standard vector in R2, which is 1 0 and 0 1, by finding the scalars such that E1 equals to C1 alpha 1 plus C2 alpha 2. And when you find it, you're able to see that it actually, these scalars is just the same linear combination, so you already know where T10 will be sent to. And the last example will be a linear transformation from Fm into Fn is uniquely determined by the sequence of vectors beta 1 where beta 1 is sent to in Te1. E1 is the standard vector in Fn. So in short, T is uniquely determined by the images of the standard basis. And you can determine this by just taking alpha, which is some coordinate vector, and then you just T alpha it, and you just replace all the alpha here with the beta 1 to beta m. And if B is a m times n matrix, then which has the row vectors of B beta 1 to beta m, this says that T alpha must equals to alpha post multiplied by B. Or if you can think about it, you can just think of this as the column vectors, and then it's just T alpha equals to B times alpha. And in other words, it means that if beta I is this, then T of this is this coordinate times this matrix. So actually, a linear transformation from Fn into Fn can be represented by a matrix. So more properties is that if T is a linear transformation from V into W, then the range will be a subspace of W. And you can just verify that as so by checking that it's closed under scalar multiplication and addition. And if you can also check that the vectors that are sent to 0 will be and you collect all these vectors together, it will form a subspace as well. And so there are some names for this, and that is called the null space. So the null space is the set of all vectors such that T alpha equals to 0. If V is finite dimension, then the rank of T, which is the linear transformation, is just the dimension of the range of T. So it's the dimension of this vector space, the range. And the nullity is the dimension of the null space. And this is a pretty big theorem. It is the rank nullity theorem. And it says that the rank of the linear transformation plus the nullity is just the dimension of V. Well, to put it into perspective, we can just prove it. So we know V is a finite vector space. So any subspace will be finite. And we take N, which is the null space. We just have a basis for it. Then the vectors, there will be K1 plus K alpha K plus 1 to alpha N in V, such that alpha 1 to alpha N is a basis for V. And now we'll just need to prove that T of this will become the basis for the range. And of course, T of everything will span the range, since anything less than K will be equals to 0, and this spans the range. So to see that it's a basis, we just need to show that they are independent now. So we just take the standard way by definition equals to 0, and I want to show that the scalars must all be 0. So this means that you can pull out the transformation because it respects linear combination. And this vector is a vector that, and according to the vector, it's in the null space So because this equals to 0, so since alpha 1 to alpha K form a basis, there must be some scalars that equal. And then you just need to take this, minus away this, and because all the alphas are linearly independent, it means that all these scalars must be 0. And hence, this shows that this forms a basis for the range. And if R is the range, then the fact that this forms a basis for the range tells us that R is N minus K. And since K is the nullity, this shows, you can just bring this over, and this shows that rank plus nullity equals to the dimension of V. So it's a very straightforward proof, but a very powerful result. So what you need to take note of the proof is that you have a basis for the nullity, for the null space. You know that you can extend it to a basis for V, and you just need to show that the remaining vector not in the null space forms a basis for the range. I hope this helped in understanding the proof for the rank nullity theorem. That's all for this video, and I'll catch you in the next one. Bye!